Episode 5 of the World of FPGA podcast. After the insight into the world, we will delve a little deeper and take a fundamental look at the structure of an FPGA. Welcome to the World of FPGA podcast. I'm your host, David Kirchner, and I will lead you through the world of FPGA. And now, let's begin. Hello and welcome back in the podcast from the world of FPGA. Well, my voice isn't as good as I want to have it, but after 2 weeks with no podcast, I thought today it's time to record some new episodes. And today there are some FPGA basics for your ears. It is more or less for a basic understanding, and it is general and not manufacturer dependent, because this kind of structure is similar, more or less similar on every FPGA. So, the basic structure of an FPGA. First of all, we have logic cells. Here is where all the logic magic is happening, and I go through the basic structure and then into every single thing or in every single point later on. So after logic cells, we have connection cells, also called the routing matrices. We have a clock network, or better, clock networks. We have some kind of storage inside these FPGAs. We have computing cells, and there's also connection to the outside world. Well, now we go deeper into every point I've talked about the last seconds. So the structure of logic cells. Logic cells consist, first of all, of lookup tables. And this is special if you have the older things like PAL, PLA, or GAL in mind. Then they have no lookup table. They have logic cells connecting. For example, we have AND cells and OR cells and can connect them together to a equation. And FPGAs have lookup tables. Lookup tables can have 4, 5, 6, 7, or 8 inputs. This is always dependent on the FPGA series or FPGA manufacturer. And you can create Boolean operations with this kind of lookup table. In hardware, it is more or less a kind of mini-ROM. So you have the inputs are your address lines, and the output, it's normally 1 or at the maximum 2 bits, which represent the output. And you have just a truth table inside of this lookup table. And for example, if you want to have an AND with 4 inputs, well, then you can say if one of the 4 inputs are 1, then the output goes 1, and if it's not so, then it goes to 0. Or you can build up just a simple inverter or other logic Boolean components, but also other kinds of logic things. The logic cells consist not only of lookup tables. We have also flip-flops, so some kind of 1-bit memory, and this is also dependent on the series and on the manufacturer. You have 1, 2, 3 or more flip-flops in one of this logic cell. Then there is always some kind of carry logic, what we need if we want to build up counters or adders or something like that. Because if we have a logic cell with 2 flip-flops, we can count inside the cell from 0 to 3. If you want to count to 4, you have to shift this bit to the next logic cell, and this is where the carry logic is used for. is always going through numbers of logic cells, so it's not possible to build up extremely big and fast counters because of runtime of the signals. But it is possible to build stacked counters, for example. So the the logic cell has also some kind of multiplexers to select different signals. For example, for the flip-flops, we have some asynchronous logic for set and reset of the flip-flops for the memory. If you want to have a global asynchronous reset, then this is the right connection we can use. And as I mentioned, all these elements are factors for FPGA manufacturers. Some have more lookup tables, some have more flip-flops, and it's always a funny thing of mixing. And the most time it is not so extremely important because the synthesis and the implementation tools from the FPGA manufacturer will choose the correct use of all these elements inside the logic cell. Now we come to the next point, the connection cells. Most of the inputs and of the outputs from these logic cells are connected to such kind of connection cells or routing matrices. There are different names. And inside these connection cells, we have predefined routes to connect the output from one logic cell with the input of another logic cell. And between this, we have our routing network. So there are connections between the connection cells to route signals between different logic cells or a group of logic cells. We are using predefined routes. We cannot create like an PCB designer drawing our own routes. We have a fixed silicon we are using, and this fixed silicon is programmable inside the logic cells and inside these kind of connection cells. So we can choose where the signal will go and where our input's coming from and where the output's going to. But we are not completely free in this kind of connection. But also this connection will be done by the routing tool from your FPGA manufacturer. And yes, there are partially specialized paths, for example, for clock networks. These clocks are not using the normal routing. They have their own network. And as the last point, this kind of nodes can be programmed. It is programmed via the bit stream we are loading into the FPGA. And it is, it's the programming of the FPGA, I would say. So the nodes, the connection cells, get the information which signal from the cell goes to which routing in the FPGA. Then next we have our clock network. Well, it is common everywhere in every FPGA that we have such kind of clock network where our clocking signals we are needing in our FPGA design is routed through the FPGA. Most time we have a central clock network. Often there are several lines in parallel, so we can choose from different clocks inside our design if it is needed. And the clock network is often divided into areas on the FPGA. So it could be that we have a one clock area on the top left of the FPGA, and on the bottom right we have another kind of clock network, so some kind of local network. The aim of the clock network, and this is important, we want to have the rising edge arrive at the same time at all flip-flops. We want that our flip-flops are always switching at the same time, so that we have some we need some time for the routing through the FPGA. The signal has to go from point A to point B, and this takes time. And if it takes too long, we cannot speed up our design in a way we want to have it. But if the flip-flops wouldn't switch at the same time point, we could get metastabilities, or we cannot reach high frequencies. And this goal is reached through some kind of tree-like network or H-shaped network. So we always divide one point of the network into 2 or 4 with the same length, and then we are using this kind of multiplication. So at the end we get an equal length of the clock line from the clock source to the flip-flops. And this is a quite difficult goal to reach, because you have, on the one hand, the length. You have to drive these lines. If you have more flip-flops, you have to put some amplification into this clocking network and so on. And at the end, all flip-flops should switch at the same time, but it's not always possible. Next element in the FPGA is some kind of storage. We have more or less always some kind of SRAM memory cells inside our FPGA. Most time it's not DRAM. DRAM is always, or most time, used externally on the FPGA. You can connect a DRAM and build your own memory controller inside the FPGA, or use a ready block, or your FPGA has a memory controller. Well, there are different ways, but inside your FPGA you have SRAM cells which have a very high speed, because we use them as FIFO. We are using them as coefficient memory for our digital signal filters. We are using them as ROM, or we're using them for parameters. And often they have some kind of error detection inside, so we can react if we have an important signal and we want to know if there's something wrong. Our SRAM cells has some kind of parity bits. And often they have different width or depth ratios, so we can have a 1-bit width and a 16 kilobit depth, for example. This is a 16 kilobit memory. Or we have calculation in mind on a live podcast. We can have 1K address depth with 16-bit width. This is also 16 kilobit, and so on. So we can create different width to depth ratios as we need it in our design. And one important thing here is the most FPGAs can be, if they are programmed with the bit stream, can initialize these SRAM cells with given values. So you put a coefficient file or an initialization file into your design, into the SRAM block RAM cells. And when the FPGA gets initialized, then this information comes into the memory. Then we have computer cells. We have adders, we have multipliers, we have connection from these multipliers and adders to the lookup tables and to the RAM. This is not a fixed cells, but it's always, if we have some kind of multipliers, you have always on the one side some kind of RAM, so you can do digital signal processing. Because if you want to have a filter, you are using the RAM for your coefficients and for your calculations, and on the other hand you have your multiplier where we want to add and multiply all the signals. And for this they are side by side in the most FPGAs, so you have a high-speed digital signal processing unit. You can use this also without these connections and use only the multiplier or only the RAM, but you can use this special connection into the with this kind of computing cells. Well, the last point are connections to the outside, and here our FPGAs are the masters of all chips I know, because all the pins are more or less universal. There can be an input, there can be an output. They have various numbers of standards they are support. They can use in a different way, for example, for single-ended signals, for differential signals. And they have adjustable drivers, so we can set up the current we want to use. Often we can select the signal standard. If we have a special standard for single-ended connections, SSTL, or for example, low voltage CMOS or something like that. Yeah, this is the one big thing from these FPGAs that we have. We can go from the layout. We can start on the layout from the PCB and then connect the lines in an optimal way. And after that, we can choose the right IOs inside the FPGA for the layout. And we have a good straightforward layout and rearrange the pins inside the FPGA later on. This is possible. And this is a thing you should always have in mind if you are doing a layout or a PCB with an FPGA. So, till this point, it was more or less common for most FPGAs. In the next episode, I want to talk about some specialties of FPGAs. Some are dependent on manufacturers, some are dependent on the FPGA series you want to use. So that's all for today's episode. All links and further information can be found at world-of-fpga.com/WFP005. If you found this episode helpful, please rate it on Apple Podcasts and share it with your colleagues and friends. That's the end of today's podcast episode. Thank you for listening and for your attention. So I say goodbye here next time, your David Kirchner.